All right, 3.2. In 3.1, we talked about measures of central tendency. So where does the center of our data set lie? In 3.2, we're going to talk about the spread or the dispersion, how spread out our data is. And we need both pieces of that information in order to get an accurate picture of our data set. So we're going to start by talking about the most basic measure of spread, and that's the range. That is simply the minimum or the maximum number minus the minimum number, and that gives us the range of our data. Suppose you ask males who have a driver's license, what is the fastest speed they have driven in the past 6 months? The slowest speed recorded is 65, and the highest speed recorded is 165 miles an hour. Find the range. Well, range again, high minus low, and that gives us 100 miles an hour. So our range is 100 miles an hour. That is the most basic, simplistic way of talking about spread. It has nothing to do with our data points to begin with. So it doesn't matter, like if a spread of 100 could be a lot, it could be little. If we're dealing with, instead of speeds that are on a highway or how fast a car has been driven, say we're talking about the speed of particles in a particle accelerator. So we talked about the Large Hadron Collider, which is a particle accelerator. They speed very small particles up to close to the speed of light, and then they crash them into each other, and they see what happens. Now, those things are going tens of thousands of miles an hour. Like they're going extremely fast. So if you had a difference of 100 miles an hour when you're talking about those incredibly fast speeds, 100 miles an hour isn't anything. That's a percent difference, which is well within like the margin of error of simply measuring how fast the particle is going. Whereas if we talk about driving a car, 100 miles an hour in a car is extreme. Like the fact that the range is 100 miles an hour, that's a huge spread of data for a car speed. So range, while it does give us some useful information, isn't a very good measure because it necessarily depends on how big your original data set was, and your range doesn't take that into consideration. More powerful values for spread and dispersion are going to be our variance and our standard deviation. Those two numbers are related. We talked about them at the beginning of 3.1, where standard deviation is simply the square root of variance. And it's weird because in our calculations, you'll see that we find variance first. And then once we find the variance, we take the square root of it to find standard deviation. But when you look at our labels, our label for standard deviation is either sigma or s. And then for variance, it's sigma squared or s squared. The reason about the variables showing that it seems like standard deviation comes first is because standard deviation is a much more commonly referenced measure of dispersion. It is the variable or the statistic that most people use when talking about the spread of data. And so because of that, that's why we give it the sigma or the S variable, and variance, much less commonly used, we make that one the sigma squared. So standard deviation refers to how spread out the data is. The larger the standard deviation, the more dispersed the data set. So here we have two data sets. Each of those data sets has 10 points in it, 10 data points, and the average of both sets of data is 40. This is why we need to have at least two different ways of talking about data. If we just say the average of both of these is 40, people might assume, well, that means they look the same, but they clearly don't look the same. And so we need to have another descriptor about our data set that talks about how spread out it is so we get a more complete picture. So what do you notice about the range and the dispersion of the data, and which do you think will have a larger standard deviation? So first, go ahead and find the range for both of these, and then tell me which one you think will have a larger standard deviation. So let's look at A. A has a max of 43 and a min of 38. So 43 minus 38 equals 5. So set A has a range of 5. Let's look at B, where we have a 47 and a 33. So 47 minus 33. We have a range of 14. So B has a larger range. Which one of those do you think will have a larger standard deviation? So if we have a larger range, most of the time we are going to have a larger standard deviation. Not 100% of the time, but there's a very strong correlation between range and standard deviation. So the larger the range, the larger the standard deviation. STD is short for standard, and then DEV is the abbreviation for deviation. So that's standard deviation. So we think B is going to have a larger standard deviation. Now, I know how to calculate this. You don't yet. So I'll tell you what these blank answers are. Set 1 has a standard deviation of 1.49, and set B or set 2 has a standard deviation of 4.99. Now, you don't know how to calculate that yet, but you will in a second. So that does, in fact, support our answer that set 2 has the bigger standard deviation. And then part C, and I like this question. What do you think the standard deviation of a data set where all 10 values are at 40, what do you think that standard deviation would be? Take a second, think about it. Okay. So again, when we talk about standard deviation, the word deviation comes from deviate. So how far away from something are you? And so that how far away are you from something, that's something we're looking at is the average. So how far away are you from average? That's what we're talking about when we talk about standard deviation. Well, if all 10 data points are at 40, our average is 40, how far away from our average are any of the data points? Well, if they're all exactly equal to our average, then the standard deviation would equal 0. And that is because there's no variance or deviation of the points. In order to have standard deviation or variance, you need to have points that vary from the average. And if they're all the average, there is no variance, there is no deviation, and so those are going to be 0. Now we're going to get into the calculation, how we find it. So we start with variance, and the variance is the average of the squares of distance each value is from the mean. So that's the English way. In a second, I'll show you how we translate that English statement into a mathematical equation or a mathematical statement. And then standard deviation is the square root of variance. So once we find the equation for variance, we just put a square root over the top of it and it becomes standard deviation. So these are the two formulas. That top formula is for variance. That bottom formula with the square root around it, that is the standard deviation. Again, they're the exact same formula with the addition of a square root around the standard deviation piece. Now, again, let's talk about where all of this comes from. So in the top part, on this inside piece here, where we have x minus mu, remember x is a data point. So we have a bunch of different x's. Every single data point is an x, and we're doing x minus mu. So mu is the average. So x minus mu tells me how far away from the average each point is. The next step of that is I square that number. The reason I square that number is because I don't want a point that's 5 below the average and a point that's 5 above the average. I don't want those 2 points to cancel each other out and be like, oh, awesome, now I don't have any deviation. Those 2 points need to compound. They need to add up with each other. And so to do that, we use the square sign because that turns everything positive. There's another type of calculation called absolute deviation or absolute variance. And instead of squaring, this time they just use the absolute value signs. It accomplishes a similar thing. It's getting rid of the positive and negative sign, but it is not extremely commonly used. You may have seen it in geometry. Absolute deviation is talked about in geometry sometimes. Standard deviation is going to be the most commonly used one in statistics, in college classes, things like that. So we find how far away you are from average. We then square that. Now we do that for every single data point. So when we talked about set 1 and set 2, there were 10 different data points. So we're going to have 10 differences. So we're going to do x minus mu 10 times. We're going to square all 10 of those answers, and then we add all 10 of those answers up. That's the numerator part. So we find the difference, we square it, we do that for all of the data points. That's what that summation sign means. And then once we've added them all up, we want to find the average of it. And so to find the average, we divide by the population size. So that's that capital N. Then after that, if we want to go from variance to standard deviation, we then have to take the square root of that answer. So that's the formula we use for both variance and standard deviation of a population. However, we very rarely have an actual population of data. Again, as we talked about in chapter 1, having a population is very difficult to get all of the data for. So typically, we'll be using the formula for sample. And the sample formula is very similar, but there's a few key differences. One difference you'll see that's very easy to see is we no longer use mu, we now have x bar. They're still referencing the average, so the concept is still the same. However, because we're dealing with the sample, we need to make sure we're using the right variables. The other difference, and it's the key difference, is the denominator. You will notice that the denominator before, when we were dealing with a population, was n, whereas here, it is lowercase n because, again, it's a sample, but it's -1. And this n-1 concept shows up in several places. N-1 is called your degrees of freedom. And essentially what degrees of freedom means is how many of the variables do you need to know? And it's the idea of, and we'll get into it again later, but it's the idea of if I know what my average is, so let's say my class average for a test was a 50%, and I had 4 people take the test. So I'll write this down. So let's say my sample average is 50. And I know I had someone that had a 40, a 45, and a 60. Now I had one other student take the test, but I can't remember their score. Can I find out what their score is based on the information I have? I know 4 people took it, I know the average is 50, and I know 3 of the test scores. Yes. If I know the average, the 3 test scores, I can find the fourth one out, and the fourth one has to be 55. Which means if I know the average, then I have n minus 1 answers that can change. Meaning these three scores can be whatever they want. But once I know those 3 scores, the fourth score is predetermined. If my average has to be 50, those first 3 scores can change, but then the fourth one has to be a certain value in order to make the average 50. And so that's why it's n minus 1, and that's why it's referred to as the degrees of freedom. I have n minus 1 things I can change, and once I've made those changes, then the fourth option, the fourth thing in my set, has to be a certain value. And so that's what a degree of freedom is, and that's what we use here, that n minus 1. Other than that, the formulas are the same. So we'll go through and we'll do a couple or an example of doing this by hand, and then I'll go through and I'll show you how you do it on your calculator as well. This talks about n minus 1 and talks about why it's basically what we just talked about. So finding standard deviation by hand, you can see there are 6 steps to it, and we are going to do those 6 steps for this data set that we have down here with 4 data points. The larger the data set, the more quickly finding standard deviation by hand becomes more and more difficult. But starting off with 4 is not too bad, so we'll go ahead and do that. So step 1, find X bar. So we add up all 4 data points, we divide by 4, and we get an average of 70. Next, for step 2, and here I'm actually going to start making a table. So I'm going to have X minus X bar. And first I start with X. So my table, I'm going to have 62, 68, 74, 76. Those are all of my X's. The next column in my table is going to be X minus X bar. So that is 62 minus 70. So I get negative 8. And then 68 minus 70, negative 2, positive 4, positive 6. So that is step 2. I find the difference or how far away each data point is from the average. Column 3, I'm going to take that X minus X bar that I just found. I'm going to square it. That's step 3, square the differences. That gives me 64, 4, 16, 36. Then I'm going to do step 4, which is sum those differences. So this is actually steps 2 and 3. Step 4, I'm going to add all of those values together, and I get 120. So that is the numerator of my equation. Remember, if we go back to our original equation, right here, the sum of, well, I've now done the sum of X minus X bar squared. So that's the numerator piece of my equation. Step 5, I take that numerator piece and I divide. And I divide by 3, which is n minus 1. N is 4 because I have 4 data sets or data points in my data set. And so n minus 1 is 3, which gives me 40. And then my final step, step 6, is to take the square root of 40, which is approximately 6.32. So standard deviation of that data set is 6.32. The variance sigma squared, or S squared, is 40. So the variance is 40. The standard deviation is 6.32. All right, next, this walks you through how to do what we just did on our calculator. And for our next problem, I'll actually go ahead and show or talk about how to do that. So let's quickly find those three pieces of information using our calculator. It's the same data set we just had, so we already know what that information is. So here, assuming it's from a sample, that means our X bar is 70 because we found that. Our median, because it's an even data set, I would average those two values together, which I believe would get me 71. No, that can't be right. 72. No, I was right. 71. And then we just found standard deviation to be 6.32, and we found S squared to be 40. All right. Now with our larger data set, this bigger data set, we are going to use our calculator to find this. So get your calculator out. It should look something like this. And we are going to go into our stat menu. And it should look like that. Then we're going to go into number 1, which is edit. And you'll see that you have a list of lists. So you have several lists here. I go L2, L3, L4, L5, L6. All of those are different lists. You can see I'm missing a list. I don't have list 1. Most of you should have list 1. And if you keep pushing to the right, if you don't see it, it should show up. If you ever accidentally delete a list or you don't see list 1 or list 2, something happened to it. Hit second mode, which quits you out, gets you back to the home screen. Go back into stat and then go to number 5, which is setup editor. Scroll down to here, hit enter again. It'll say done. Now when we go back to that stat edit, now you can see I have L1 and it has all of the numbers that were in it before I deleted it. So that's another nice feature. Even if you accidentally delete it, if you put a bunch of numbers in there, they will still be there. I want to use list 1, so I want to clear that list, but I don't want to delete it. So if you scroll up, so where now the L1 is highlighted, if you hit delete, DEL, it will erase the whole list and you'll have to go back to that setup editor. We don't want to hit delete, we want to hit clear. So we hit clear, then we hit enter, and that erases all of the stuff that was inside of that list. Now I'm going to enter all of the numbers into my list. So 40, 38, go through, enter all of those numbers into your list. And it looks like I have 9 entries. So again, checking here, the same thing I'm going to tell you to do when we did frequency. Check to make sure you have the correct number of entries. I have 9 numbers. I'm going to count how many I should have. I should have 10. So I missed one, and it looks like when I went back here and just put 39, I made 2 mistakes. So that should be 40, then 39, then 40 again. The most common mistake when dealing with statistics or large data sets in general is data entry errors. Just hitting a wrong number on your calculator. Take time, look at the numbers that you are entering, go back, double check them, count to make sure you have them, scan them over, make sure you didn't add an extra 0 or an extra 1 to something. Be careful, because if you put the numbers into your calculator wrong, obviously everything else is going to be wrong too. So we now have our data set, which is fantastic. So we now hit mode, quit, or second quit. And in order to find all of our statistics, we're going to go to stat and calc. Calc is short for calculate, and we're going to look at one var stat, and that is one variable statistics. This one variable statistic is going to give you a whole bunch of different statistics about one variable. And that's all we have. We only have one list, which is our one variable. So we're going to hit enter. And then we're going to look to see what information it needs. It needs the list. So we put all of our information into list 1. So I'm going to clear out list 3. I don't want list 3. Then I'm going to hit second and 1. That brings up L1. I'm going to make sure my frequency list is blank. I'm going to scroll down to calculate. I'm going to hit enter, and it pops up with all of the different statistics I could want. It has X bar, which is my average. It only shows X bar, but X bar and mu are the same thing, so that's why it doesn't show both of those. That's my average. It shows me both S and sigma, so it shows me both my population and my sample standard deviation. And then if I scroll down, it shows MED. That is my median. So it shows me all of the good pieces of information that I need. So let's go back to our notes. Assume it's a sample, find the mean, the median, the standard deviation. So mean, 40. Median, 40. Standard deviation for a sample was 1.49. Then it also wants the variance. In order to find the variance, you have to square the standard deviation. So 1.49 squared, S squared is 2.22. Now it asks for the same information, but for a population instead of a sample. So instead of X bar, we now have mu, but mu is still 40. Our median is still our median. Now the difference is going to come when we talk about standard deviation. We are now dealing with sigma, and our standard deviation is now 1.41. So we go back here and we see the difference between S sample and sigma population. And so you have to be very careful about whether or not your data set is talking about a statistic or a sample or a population when dealing with standard deviation. And then again, for our variance, sigma squared, 1.41 squared gives us 1.9, rounded to 1.99. All right, so that's how we use our calculator. Make sure you're practicing that. We'll be using our calculator more and more as we continue throughout the semester. Next, when we're talking about spread, we are also going to be talking about the empirical rule. The empirical rule is an incredibly useful piece of information that works when we're dealing with a normal distribution. If it's not normal, if it's skewed left or right, or if it's binomial or bimodal, or if it is uniform, then the empirical rule does not work. However, as we will find out when we get into chapter 7 and chapter 8, there are ways of turning any distribution of data into a normal distribution. And so because we can turn any distribution into a normal distribution, this empirical rule is a fairly powerful and quick way of talking about the spread of a data set. You may also see it if you go to Wikipedia or look online as the 68, 95, 99.7 rule. And what it's talking about is how much, what percent of the data falls in between a set of standard deviations. So 68% of data will fall within one standard deviation of the mean. So if you start off at the mean and you add and subtract one standard deviation, so you get a interval of numbers, If it is a normal distribution, 68% of the data will fall between 1 standard deviation below the mean and 1 standard deviation above the mean. And then 95% of the data will fall within 2, and then 99.7 within 3. And then this is that visual representation where we start with the average, and then these are standard deviations. So we add 1 standard deviation and subtract 1 standard deviation, and that gives us 68% of the data. Add 2, subtract 2, 95. Add 3, subtract 3, 99.7. Now, we're going to be using this concept for the next 2 example problems, and that will wrap up this section. So first, using this graph, attempt to answer these 3 questions, A, B, and C. When you've attempted them or you've looked at it and kind of given it a thought, unpause, come back, and we'll go over it as a class. All right, so looking at this graph, based on the graph we saw above, that value in the middle, because it's a normal distribution, is going to represent our mean. So X bar is going to be equal to 490, because that's the value in the middle. Then again, if we go back up here, the distance between those 2 things, that is our standard deviation. So if we go from 490 over to 590, that would make our standard deviation 100. So that is the center and the spread of our distribution. Then it starts asking us questions about how much data lies between different things, and this is how we use that empirical rule. So what percentage of the data lies between 190 and 790? Well, we start with the center, we start with our median, and we go, okay, that's 1 standard deviation, 2 standard deviations, 3. So I'm at +3 standard deviations above the mean to get to 790. Now let's count how many standard deviations I am below the mean to get down to 190. So 1 standard deviation below, 2 standard deviations below. So that's 3 standard deviations below. So I'm 3 below and 3 above. We look at that and we see that if we go from 3 standard deviations below all the way to 3 above, that is going to be 99.7% of the data. Questions on that? Awesome. If you have questions, always use that help button. Let me know, and I can go over or clarify anything that you guys have. Next, what percentage of the data lies below 390? Couple different ways to look at this one. The first one I think is the easiest is I always start off with, okay, if I'm looking at a below, I'm going to cut off as much as I can as early as I can. So I'm going to split this in half, and I know I'm not talking about any of this data up here. How much of the data is above the median? Well, if the median and the mean and a normal distribution are right in the middle, that means there's 50% of the graph. This way is 50%, and this way is 50%. So I know I have no more than 50%. Half of my graph is cut off. The next step I'm going to look at is, okay, well, how much of the graph is in this blue area here? So I go up, oh, that's 34%. So that means I started out at 100%, and I didn't have any of the right side of the graph, so I subtract 50%. And then I also didn't have that blue chunk on the left half, which was 34%. So I subtract the 50, I subtract the 34, and that gives me what's left over, which is 16%. So 16% of my data lies to the left or below 390. All right. So now we're basically doing the inverse of what we just did. Here I'm giving you the data. I'm telling you the mean, I'm telling you the standard deviation, and I want you to find me the cutoffs, the limits for the different percentages. 68, what is my interval? 95%, what's my interval? 99.7. And then you're going to draw a picture similar to the picture we just looked at here. So pause the video, try to do those 4 problems, and we'll go on. All right, so first, my average is 7.5. My standard deviation is 1.13. All right, so I've got my average, I've got my standard deviation. 68% of the data, that is x plus s and x minus s. So 7.5 plus 1.13, that will give me my upper limit. And then my lower limit is 7.5 minus 1.13. So that is the interval that will contain 68% of my data. For the 95% interval, I start with x, but I go plus 2 times s, and x minus 2 times s. So I multiply my standard deviation by 2, and then that's the value I'm adding or subtracting to my mean. So 95% of the data falls between 5.24 pounds and 9.76 pounds. And then for part C, again, the same pattern exists. However, this time I am multiplying my standard deviation by 3 before I add and subtract it from my average. And that gives me 4.11 and 10.89 pounds. And then the last piece is simply making our drawing. So we would go through. In the middle, you would have 7.5. And then we would have our first 2 cutoffs. Then we go further out, and we have our second 2 cutoffs. And then way out here on the edge, we have our last cutoffs. And then if you wanted to make it look like that picture, you could color in those sections differently. So you could make these 2 middle sections red, and the red would incorporate 68% of your data. Make the next section blue. And so if you look at the red and the blue, you're talking about 95% of the data. And then if you look at the red, the blue, and the green, you'd be talking about 99.7% of the data. And that is the end of 3.2.